In section 2.2, we are going to continue our discussion of functions. After studying this section, you should be able to identify the intervals on which a function increases, decreases, or is constant. Use graphs to locate relative maximas or minimas. Test for symmetry. Identify whether a function is even or odd or neither, and recognize the symmetry. Understand and use piecewise to find functions, and find and simplify a function's difference quotient. Let's first look at increasing, decreasing, and constant. Suppose for some reason you decide to track your temperature when you wake up with a fever. So at 8 a.m. when you wake up, your temperature is 101 degrees. 3 hours later, at 11 a.m., your temperature has decreased to what is seemingly normal. So from 8 a.m. to 11 a.m., over those 3 hours, your temperature has decreased. As you can see over that interval, the graph of my function is falling from left to right. It's going down. As x gets bigger, y is getting smaller. As x gets bigger, y decreases. At 11 a.m., you've taken your temperature, it seems to be normal, and you wait 2 hours to take your temperature again. So 5 hours after 8 a.m., at 1 p.m., you take your temperature again, and now it's 100 degrees. So in those 2 hours, from 11 a.m. to 1 p.m., your temperature has increased. Looking at the graph, you can see from time x equals 3 to time x equals 5, the graph has gone up. It has risen from left to right. Or, as x has increased, so has y. So from 3 to 5, the graph of my function is increasing. At 1 p.m., you took your temperature, it's 100 degrees. You wait 2 hours and you take your temperature again at 3 p.m. And at 3 p.m., your temperature is still 100. So from time x equals 5 to time x equals 7, your temperature has remained constant. It hasn't risen or fallen, it's remained constant. All right, let's get an algebraic definition of how a function's increasing or decreasing behavior. A function is increasing on an open interval, and let's pause and talk for a second. What does this mean for an interval to be open? That means we don't include the endpoints in the interval. This is the case where you have open circles on the end of each interval, or perhaps the interval is going indefinitely to the left or right, so going to infinity or negative infinity. But it means it's open. You never include the endpoints when you're describing the intervals over which a function is increasing, decreasing, or constant. You never use brackets when you're writing these intervals in interval notation. You only use parentheses. All right, let's continue. A function is increasing on an open interval I if the value of the function f of x1 is less than f of x2 whenever x sub 1 is less than x sub 2. So what this means is that the function is going up. It's rising from left to right. So if this is x sub 1, this is x sub 2, when x sub 1 is less than x sub 2, so is the value for y. So at this point here, the y value is smaller than the point where x is equal to x sub 2. So this means that the graph is rising from left to right. A function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x sub 1 is less than x sub 2. This actually means it's falling from left to right. So as x gets bigger, y is getting smaller. So the value of y at x sub 1 excuse me, is bigger than the value of y at x sub 2. And a function's constant on an open interval, again, you're describing increasing, decreasing, and constant over intervals that are open. You never use brackets. A function is constant on an open interval, I, if f of x1 equals f of x2 for any x1 and x2 in the interval. That means the value of y is constant. It doesn't change over that interval. And again, not to reiterate it enough, the last statement on this slide says you never use brackets when describing the interval over which a function is increasing, decreasing, or constant. All right, so let's see if we can't determine where this function is increasing, decreasing, or constant. So I probably need to identify these points here. And these points are where the graph of my function is actually changing direction. And we'll talk about maximas and minimas in just a second, but that's what these are. So let's label this point -1, 1. And let's label this point 1, -1. All right, so first of all, looking at this graph of this function is never constant. There's no part of this graph where the line is horizontal. So this function is never decreasing. We need to have a portion of the graph that's flat. So as x gets bigger, y remains constant. So we would have a horizontal part of the graph. We don't have this here. So this function is never decreasing. All right, so where is it increasing? A function is increasing if its graph is rising from left to right, or as x gets bigger, so does y. So there are two areas of this graph where the function is increasing. The first place that it's increasing is to the left of x equals -1. Over here to the left, it's increasing. And then when it hits that point, I need to write that as an open circle. It's getting closed up. So let me erase that and try that again. So at -1, the value of the function is 1. At x equals -1, the function's y value, it's the value of the function, is equal to 1. So to the left of that point, the function is increasing. Now what happens when it hits that point? At that point, the function starts changing direction. And now it's no longer increasing, but it's decreasing. So it's decreasing between the point -1 and the point 1. So let's draw a circle here too. So it's decreasing where I shade this in blue. It hits the point 1, -1. At x equals 1, the value of the function is -1. Just to the right of that point, the function starts increasing again. So it's increasing to the right of positive 1. Let's shade that in red. So again, the function is increasing to the left of -1. When we describe the intervals over which a function is increasing or decreasing, we always describe it over the domain of the function, over the x values. So the function is increasing to the left of -1. It hits x equals -1. At x equals -1, the value of the function is 1. Just to the right of that point, it starts decreasing. It decreases until it hits the point x equals 1. At x equals 1, the value of the function is 1. Just to the right of x equals 1, the function starts increasing again. So the function is increasing to the left of -1. So how do we describe an interval to the left of a constant? We describe that interval as starting at -infinity, although we know it doesn't actually start at -infinity. That's a concept, not a number, but it is going indefinitely to the left. So the way we describe that is we say the interval over which it's increasing is from -infinity to -1. It's also increasing to the right of +1. So the way that we describe an interval over which the function is indefinitely going to the right, or the interval is going to the right indefinitely, I will spit it out, we describe that as saying it starts at 1 and it goes to infinity. Now, what do we put between those two intervals? Now, typically we would put a union symbol because that is the union of those two sets. In some of your homework, they're just asking you for a comma between the two sets. So be sure to read the instructions on the problem you're working so that you'll know how to input your intervals, either using a union symbol or a comma. All right, where is this function decreasing? The function is decreasing where it falls from left to right, and we already shaded that in blue. It's falling from -1 to +1. All right, so let's stop and talk for a second. You'll notice that all these intervals are open. I'm never using a bracket anywhere. When we discuss increasing, decreasing, and constant, we always refer to a function's increasing, decreasing, or constant over an open interval. So no brackets. The other thing that we notice is that we're discussing these intervals over the domain of the function. So we always use x values to describe the intervals over which a function is increasing or decreasing or constant. So this function is increasing in the x direction. It's increasing from -infinity to -1 over the domain. It's decreasing from -1 to +1 over the domain. It's increasing from 1 to infinity over the domain. Okay, relative maximums and minimums. A function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in an open interval. Okay, what's this mean? Okay, it's a relative maxima at that point if on each side of the point, the value of the function is smaller. A relative maximum is a hill in the graph of your function. If we look at this relative maximum, on each side of that maximum, the value for the function, or the y value, is smaller than it is at that point. So a relative maximum's a hill because on each side of it, the value of the function is smaller. A function value f of b is a relative minimum if of f if there exists an open interval containing b such that f of b is less than f of x, such that f of b is less than f of x for all x not equal to b in the open interval. So what that means is that if it's a relative minimum, if on each side of it, the value of the function is larger. So a relative minimum is a valley in the graph of my function, because in a valley on each side, the sides are higher. So it's a relative minimum if on each side, the value of the function, the y value, is greater than it is at that point. Sometimes we use the word relative maximums and minimums instead of, we use local instead of relative. Sometimes you'll hear local instead. Okay, so let's use graphs to locate relative maxima or minimas. And you'll notice we use maximum and maxima and minima interchangeably. Okay, so what's our relative maximas or minimas? Well, I have a relative maximum right here at pi over 2, 1. And it's a maximum because on each side of that point, the graph's y value is smaller. So the value of the function is smaller on each side. And the way we state this is we say we have a relative maximum of 1. So the maximum or minimum value is its y value at x equals pi over 2. So the maximum or minimum value is the value of the function at that point, and it occurs at that input x. So we have a minimum over here. We have a minimum of -1, and it occurs at negative pi over 2. So the way we state that is we have a relative or we could say local, that's used interchangeably, minimum of -1, and it occurs at x equals negative pi over 2. So when you put these into MyMathLab, you're only going to put just the value of y. So the minimum is -1, and it occurs at x equals negative pi over 2. Right, so what is our relative maximum or minima here? So this is the graph we looked at just a minute ago for increasing and decreasing. So let's go ahead and label this was -1, 1. We labeled it before. And this is 1, -1, that point in blue. And we have a relative maximum at -1, and its value is 1. So we have a relative maxima of 1 at x equal -1. And we have a relative minima, of -1 at x equals +1. All right, so why is this important? Because relative maximas or minimas tells us what the function's doing on each side of it, whether it's increasing or decreasing. If you have a relative maxima, to the left of that relative maxima, your function will be increasing. It hits that relative maxima, and then to the right of that relative maxima, it will start decreasing. So to the left of a maxima, the function is increasing. To the right of a maxima, the function is decreasing. We hit the relative minima at 1. When we hit that relative minima, to the right of that relative minima, the function is increasing. To the left of that relative minima, the function's decreasing. So this function is increasing. It hits its maxima. It changes direction from increasing. It starts decreasing. It decreases till it hits its minima. It changes direction, and it starts increasing. All right, let's next talk about symmetry. And this is a photograph of Denzel Washington. And I've been told by folks that have studied art that he has a perfectly symmetrical face. So what constitutes an attractive human face? It's symmetry. So in this photograph of Denzel Washington, we've drawn lines between paired features. And notice how his features line up almost perfectly. Each half of his face is a mirror image of the other half of his face through the vertical line that we've drawn through his nose. If we superimpose a rectangular coordinate system over his face, we notice that there's a point XY on the right of our vertical axis that corresponds to a mirror image point, negative XY, on the left. This figure is said to be symmetric with respect to that vertical axis we call Y. The graphs of some equations exhibit exactly the same kind of symmetry as Denzel Washington's face. And the word symmetry comes from a Greek word that means the same measure. All right, so what are our tests for symmetry? So the first type of symmetry we might encounter is like the face we looked at, which is symmetry with respect to a vertical axis, which we always call Y. So if we have symmetry with respect to the Y-axis, what happens? If we have a point X that we input into our function, we output a value of Y. If I input negative X into the same function, I also output Y. So it doesn't matter if I input X or negative X, I output the same value of the function, the same value of Y. The second image here, part B, is not a function, but it does have symmetry with respect to the x-axis. It's not a function because for the input x, I'm getting two different outputs for y, one positive and one negative. But that is symmetry with respect to the x-axis. So if I input x, I output y. Also, if I input x, I output negative y. So I input the positive and I output both the positive and the negative. That is symmetry with respect to the x-axis. It is not a function. The third symmetry is symmetry with respect to the origin. If I have a function and I have a point xy that is some distance from the origin, I will have a point in the opposite direction, the same distance away on the function's graph. So if I draw a line in the opposite direction, the same length, d long, I will hit another point on the graph. Also, if I input x into my function, I output y. If I input negative x, I output negative y. That is symmetry with respect to the origin. So A and C are both functions. We can have functions that have symmetry with respect to the y-axis. And C, we can have symmetry with respect to the origin and it be a function. Okay, so how do we test for symmetry? The graph of an equation is symmetric with respect to the y-axis if for every point xy on the graph, the point negative xy is also on the graph. So the way we do the test is we replace x with negative x, and if we get the same equation, an equivalent to what we started with, then it is symmetric with respect to the y-axis. To test for symmetry with respect to the x-axis, not normally the graph of a function, if for every point xy on the graph, there's a point x negative y on the graph, then it's symmetric with respect to the x-axis. So we replace y with negative y, and we get exactly the same equation we started with. That's symmetry with respect to the x-axis. To test for symmetry with respect to the origin, the graph of an equation is symmetric with respect to the origin if for every point xy on the graph, there's a point negative x, negative y on the graph. So the way we test is we replace x with negative x and y with negative y and see if we get the same equation that we started with. Do we get the equivalent equation? So let's practice this. So let's see if x equals y squared minus 1 is symmetric with respect to the y-axis, the x-axis, or the origin. So let's first test for symmetry with respect to the y-axis. To test for symmetry with respect to the y-axis, replace x with negative x. So my original equation is x equals y squared minus 1. Now my new one with that replacement is negative x equals y squared minus 1. Are these identical? Are they exactly the same equation? Are they equivalent? And the answer is no, they are not. They are not equivalent equations. The first equation has a positive x, the second equation has a negative x. They are not equivalent. So it is not symmetric with respect to the y-axis. Okay, now let's test for symmetry with respect to the x-axis. To do this, we replace y with negative y. My original equation is x equals y squared minus 1. My new equation will be x equals, and I'm going to replace that y with a negative y with parentheses around it so I don't make a sign error. And what happens when I square a negative in real numbers? It becomes positive. So this is going to be y squared minus 1. So are these equivalent? And the answer is yes. X equals y squared minus 1 is equivalent to x equals y squared minus 1. So we are symmetric with respect to the x-axis. All right, now let's test for symmetry with respect to the origin. And to do this, we're going to replace x with negative x and y with negative y. So my original is, well, x equals y squared minus 1. So my new one's going to be negative x equals negative y squared minus 1. So it's going to be negative x equals y squared minus 1. Are they equivalent? No. So it's not symmetric with respect to the origin. All right, if we look at the graph of this relation, it's not a function. The graph of this relation is shown in these two graphs, and you can see that there is symmetry with respect to the x-axis. I do have a point on each side of the x-axis. If I input 2, I output whatever that number is. If I input 2, I also output the positive. So when I input x, I output 2 different y's. That makes it not a function, but it does make it symmetric with respect to the x-axis. Okay, specifically looking at functions and their symmetry, functions can be symmetric with respect to the y-axis, and functions can be symmetric with respect to the origin. If a function is symmetric to either the y-axis or the origin, we give them special names. A function is even if it has symmetry with respect to the y-axis. The function f is an even function if f of negative x equals f of x. So if we replace x with negative x in our function and we get an equivalent equation, that is symmetry with respect to the y-axis, and that function is even. A function is odd if f of negative x equals negative f of x. So if we replace x with negative x and we get exactly the opposite equation that we started with, that function is odd, and there's symmetry with respect to the origin. All right, let's do an example. Well, first, let's look at a couple of cases. The first case is the case of an even function. An even function, you have symmetry with respect to the y-axis. If I input x, I output f of x or y. If I input negative x, I output exactly the same thing. So it doesn't matter if I input x or negative x, I output y. With symmetry with respect to the origin or an odd function, if I input x, I output y. But if I input negative x, I output the opposite. So if I input x, I output f of x. If I input the opposite, I also output the opposite. All right, which one of these are even, odd, or neither? Graph A is symmetric with respect to the origin. If I pick a point over here on the graph, and that's some distance d away from the origin, if I go in the opposite direction from the origin, I should hit a mirror spot on the graph, and I do. So this is symmetry with respect to the origin, so this is an odd function. Symmetry with respect to the origin makes that function odd. The second function is symmetric with respect to the y-axis. If I have a point here on the graph that's some distance from the y-axis, I should have a point on the graph the same distance away in the opposite direction on the other side of the y-axis. If I do, that's symmetry with respect to the y-axis, and that is an even function. The last graph on this slide, number C, is neither. It's not even and it's not odd because I don't have either of the first two cases. If I draw a point here, that's some distance from the origin. In the opposite direction, I don't have a point. If I draw a point and I draw a line to the y-axis, some distance, I don't have a point in the opposite direction. So it's not symmetric to the origin, it's not symmetric to the y-axis, so it's neither even or odd. All right, so how do we test for this? Replace x with negative x, and if you get the exact same equation that you started with, an equivalent equation, then that is symmetry with respect to the y-axis. That's an even function. If you replace x with negative x and you get the exact opposite equation as to the one you started with, that's symmetry with respect to the origin. That's an odd function. If neither one of those things happen, then the function's neither even or odd, so it's neither. Okay, let's test to see if this function's even, odd, or neither. So the way we conduct this test is we replace x with negative x. So we're going to evaluate the function at negative x. And to do that, I replace x with negative x. Now I'm going to simplify this. When I raise a negative to an odd power, the result will be negative. So negative x to the fifth is negative x to the fifth plus 1. All right, so is this identical to my original? And the answer is no, because the original equation has positive x to the fifth plus 1. When I replaced x with negative x, I got negative x to the fifth plus 1. So they are not identical. So it is not an even function. Okay, is this exactly opposite of what I began with? Well, what would the opposite be? Well, it would be negative h of x, which would be negative x to the fifth plus 1, which would be negative x to the fifth minus 1. So how do we find the opposite? We just change the sign of all the terms on the right-hand side of my equation. Okay, is that identical to what I began with? And the answer is no, they are not identical. Oh, excuse me, not identical. Completely the opposite of what I began with. Is that opposite to what I began with? I got even on the brain. Okay, is that the opposite? Oh, just bear with me for a minute. Get my arrows going to the right place. All right, so the opposite is negative x to the fifth minus 1. What I got when I replaced x with negative x is negative to the x to the fifth plus 1. So are these two things opposites? And the answer is no, they are not opposites. The equation when I replaced x with negative x is negative x to the fifth plus 1. When I take the opposite of the function, negative h of x, I get negative x to the fifth minus 1. The difference between the two is one has a +1, the other one has a -1. So they are not opposites of each other. So this function is not odd. So since it's not odd and it's not even, it's neither. So how do you test for even or odd? Replace x with -x. If you get the identical equation to the one you started with, then it's even. If you get exactly the opposite of the one you started with, it's odd. All right, let's discuss piecewise defined functions. And I have a fondness of saying that the world is defined by a piecewise defined function. Everything almost, it seems, is defined piecewise. For example, if you earn a commission on a sales job, that's piecewise defined because lots of times you earn a certain commission up to so many sales, and if you make that volume of sales, if you go over it, then your commission might increase. So for example, if you're selling cars, if you sell 10 cars a month, I don't know if that's good or not, perhaps you earn a 2% interest on the sale. But if you go over 10 cars a month, maybe your commission goes up to 4%. So it's an incentive for you to sell more because your commission is going to increase. Bills are the same way, like utility bills or like your electric bill. If you use up to a certain number of kilowatt hours, then you're going to get charged at a certain rate. If you go over that, then the rate might increase. Water bills. If you use up to so many gallons of water a month, you get charged by a certain rate. If you go over that amount, then you're going to get charged more. So our example is going to be a telephone company. A telephone company offers the following plans. You pay $20 per month, and that buys you 60 minutes. Any time that you talk over 60 minutes, you're going to get charged 40 cents a minute for each minute over 60. So this is a piecewise defined function, and we can represent it mathematically as follows. The cost function, C of t, is equal to 20 if you talk between no minutes and 60 minutes. So if you don't talk at all, you're going to get charged $20. If you talk 40 minutes, you're going to get charged $20. If you talk 60 minutes, you're going to get charged $20. So your cost is constant as long as you talk 60 minutes or less. As soon as you go over 60 minutes, there's going to be an additional charge. When you go over 60 minutes, you're going to get charged the $20. Plus, you're going to get charged 40 cents for every minute over 60. So if you talk 61 minutes, you're going to get charged 40 cents for that 1 minute plus the $20. So you're going to get charged $20.40. So the way we represent this, the cost function, you're going to get charged a flat rate of $20 if t is between 0 and 60 inclusive. So if t is greater than or equal to 0 and it's less than or equal to 60, you get charged 20 bucks. But as soon as you talk more than 60 minutes, you're going to get charged using a new rate. And that rate is the flat rate of $20 plus 40 cents for every minute you talk over 60. This is a piecewise defined function. It's defined using a different rule depending where you are in the domain. So in this example, if you're between 0 and 60 inclusive, so you're in the domain from 0 to 60 inclusive, you get charged $20. But as soon as your value in your domain, your input in your domain goes over 60, you have to use a different rule to figure out how much your bill is going to be. For example, how do you figure out then what C of 40 is? How do you determine the cost when the input is 40? Well, the input 40 is in this part of my domain. 40 is between 0 and 60. So what rule do I use to evaluate my function if my input is 40? Well, if my input is 40, my output is 20. 40 is in the part of the domain that's defined by the first rule. So if I evaluated C of 20, it would be 20. If I evaluated C of 10, it would be 20. If I evaluated C at 15, it would be 20. Any evaluation where the input is between 0 and 60 is going to give me an output of 20. It's going to cost me $20 if I talk between 0 and 60 minutes inclusive. But how do I find C of 80? Now my input 80 is in this part of my domain. 80 is larger than 60. So I have to use the second rule to define or find the value of my output C of 80. So now I'm going to use the 20 plus 0.4. My input is 80 minus 60. I get 20 plus 0.4 times 20. And I believe that is, get my notes out so I get it correctly. I believe that's $28. 0.4 times 20 is 8. 8 plus 20 is 28. So if I talk 80 minutes, I'm going to get charged $28. If I talked 100 minutes, I would get $36, I think. 100 minus 60 is 40. 40 times 0.4 is 16. 16 plus $36. So you can see that it depends on where your input is. Is your input in the first part of the domain, the rule that says the output's 20 if the input's between 0 and 60? Or is your input in the second part of the definition? Is your input greater than 60? If your input's greater than 60, then you use the second rule to find the output given that input. That's a piecewise defined function. Now you can graph these. They're pretty easy to graph. I graphed them in pieces. Since it's a piecewise defined function, kind of makes sense that I would graph it in pieces. So this piecewise defined function is f of x equals 3 if x is less than or equal to -1, and f of x is x minus 2 if x is greater than -1. So I have two different pieces, and they're defined over different portions of my domain. So let's first look at the first piece. Let's evaluate this function at a couple of values. And we need to evaluate them at values less than -1. So what would be less than or equal to -1? -3, -2, and -1. Would those be three numbers that are less than or equal to -1? And the value of the function, no matter what the input is, when the input's less than or equal to -1, the output is 3. The output is constant everywhere to the left of -1. So my ordered pairs would be -3, 3, -2, 3, and -1, 3. Now I'm going to graph the second piece of this. The second piece is defined by x minus 2, and it's defined for x is greater than -1. Now I'm actually going to graph -1, even though -1 is not in the domain of that piece of this graph. I'm going to graph this as an open circle. And that'll just give me an idea where the graph of this part of the function starts. So I'm going to evaluate the function at -1. That's going to give me -3. Let's evaluate the function at 0. That's -2. Let's evaluate the function at 1. That's -1. So I'm going to plot these 3 points. And I'm going to plot -1, -3 as an open circle because that point is not included in this part of the graph of this piecewise defined function. So we're going to graph 0, -2, and 1, -1. Okay, so let's go plot those points. Okay, so I have -1, 3. And that is a solid dot because I have x is less than or equal to -1. So that point is included in that part of the graph. I had what? -2, 3 and -3, 3. And so I'm going to connect those. And this is going to continue to the left indefinitely because it's for all values of x less than or equal to -1. Okay, now let's graph the other part of our graph. We evaluated this at -1. At -1, we got -3. And I'm going to graph that using an open circle because that point is actually not included in this part of the graph. Then we evaluated this function at 0. We got -2. And we evaluated it at 1. We got -1. Now I'm going to draw a line that connects those dots. And we're going to draw it with an arrow because it says x is greater than -1. So it's going to continue indefinitely to the right. Okay, let's talk about domain and range. Right, what's the domain of this function? Well, if we look up here, that defines our domain. X is less than or equal to -1, x is greater than -1. So if I draw that on a number line, it's going to be the union of those two things. So it's less than or equal to -1, but greater than or equal to, -1. So if I union those two things together, then I'm going to get the set of all real numbers. So it's going to go from -infinity to +infinity if I slap those two things together. So the domain is all real numbers. Okay, but what's the range? Well, the range is a lot trickier. But as you recall, we always look at the range from the minimum value in the y direction to the maximum value in the y direction. So the minimum value in the y direction is right here. And that value is what? -3. And it's an open circle, so we're going to use a parenthesis. And then what happens? Well, it continues on forever. This arrow here not only is going to the right, it's going up. So the range starts at -3, but it continues on forever. So the range is from -3 to infinity, not including -3. Okay, all right. The difference quotient. Now the difference quotient has applications in calculus. If you find the difference quotient of a function and then you take the limit as h goes towards 0, you get the first derivative. And those of you who have taken calculus or are going to take calculus, you'll be finding the first derivative using the difference quotient. Now, I find the difference quotient by using a step-by-step process. The first thing I do is evaluate the function at x plus h. Can I evaluate a function at x plus h? Sure. I can evaluate a function at any value that is in its domain. What x plus h represents is a number ever so slightly larger than x. Infinitesimally larger than x. So h is a little bitty teeny weeny amount, and it makes f of x plus h ever so slightly larger than f of x. So I evaluate f at x plus h first. Then I subtract the function from that, and then I divide the whole thing by h, and that will give me the difference quotient. So given a function, negative 2x squared plus x plus 5, let's find the difference quotient. So the first thing I do is evaluate the function at x plus h. So I'm going to replace, everywhere there's an x, I'm going to replace it with an x plus h. Okay, now I'm going to simplify this. I'm going to square by my binomial by using the squaring a binomial formula. I square the first term, so I square x. I multiply the two terms together. I get x times h. Then I double that, multiply that by 2, get 2xh. Then I square the second, so I square the h. Now I'm going to remove my parentheses by distributing the negative 2 across those three terms inside parentheses. So I get negative 2x squared minus 4xh minus 2h squared. The second set of parentheses I can just drop. There's nothing outside of those parentheses except the number 1, so I can just drop them. And there is the first step in finding my difference quotient. I have f of x plus h. So now I'm going to take that f of x plus h and I'm going to subtract the original function from that. So I have f of x plus h minus f of x. So what I got for f of x plus h was minus 2x squared minus 4xh minus 2h squared plus x plus h plus 5. And I'm going to subtract from that the original function. So I'm going to remove those parentheses. By distributing that negative across, I'm going to get plus 2x squared minus x minus 5. Now, if I've done this correctly, everything that does not contain an h should subtract off. Okay? So I have a negative 2x squared. I have a 2x squared. Negative 2x squared plus 2x squared is 0. I have a negative 4xh, a minus 2h squared. Okay, I have a plus x and a minus x, that adds to 0. I have a plus h, I have a plus 5 and a minus 5, that adds to 0. So what I have left when I combine like terms is negative 4xh minus 2h squared plus h. Now I'm going to take that and divide it by h. So I'm going to take each one of these terms and divide it by h. Okay, in the first term, the h's will divide out, they'll cancel. So I'm left with minus 4x. In the second term, the h will cancel. I'm left with minus 2h. In the last, the h will cancel. I'll be left with, when the h cancels, I have 1 left over, so I'll have plus 1. And that is the difference quotient. And again, in calculus, if you were to find the limit as h goes to 0, so you're going to let h become 0, you'd get negative 4x plus 1. That is the first derivative of that function, FYI. And that's the end of section 2.2.